Hello and welcome to Autology, the weekly podcast that brings you the latest on automotive technology. This week's episode is called Graphene in Automotive, and you're here with me, Anna Büttner, and Edwin Pope, Principal Analyst for Vehicle Dynamics and Materials at S&P Global Mobility, alongside our special guest, Terrance Barkan, Executive Director of the Graphene Council. Hello to you both, and thank you for joining this week's episode of Autology.
Thank you, Anna. Really happy to be here. And Ed, great to be here with you as well.
Thanks, Anna, for hosting us today. And thanks, Terrance, for being willing to subject yourself to this and then chat with us today.
Yeah, great. Terrance, as our special guest, can you please give a brief explanation of what you do as the Executive Director of the Graphene Council for our audience that might be unfamiliar with the platform or community you serve?
I'd be happy to. The Graphene Council was founded 10 years ago, and today we now reach 35,000 material scientists worldwide who have an interest in 2D advanced materials, and in particular with graphene. So as the executive director, I'm responsible for overseeing all of our global operations and the work that we do in this sector, which includes setting standards, testing material, verifying producers, but mostly it's engaging with and educating potential users of graphene materials. And the automotive sector is one of those really important sectors.
All right, great. Thank you for that. So now that we kind of set the stage here, let's dive right in with my first question. What is graphene? What is it used for, and what forms of graphene have been made commercially available?
It's a really good question. And on the surface, it might seem somewhat simplistic, but it's more complicated than that. Graphene is pretty widely known. A lot of people have at least heard of graphene, and it makes it seem as though it's one material. And in fact, I encourage people to think of graphene as kind of a family of materials. The scientific definition is a single atomic layer of sp2 bonded carbon in a crystal pattern. Kind of looks like chicken wire. But you have many forms of graphene, which could include one layer of carbon, 2, 3, 4, up to and including 10 layers of carbon. And then you have other derivatives, which are really important because they change how they work in different applications. Things like graphene oxide, which is 35% oxygen by content, or functionalized graphene, in which other molecules or chemicals have been added to the surface or edges of particles, again, to change their behavior. So there's a whole range of materials that fall within the definition of what is graphene as defined under ISO standard.
Very good. Okay, taking it one step further then, what components and material groups within automotive have been proposed to benefit from graphene? Are any significant graphene components on the market currently?
Well, the most notable example of this is the Ford Motor Company, which a couple of years ago now actually had graphene enhanced polyurethane parts in the engine compartment. And this was primarily done to improve the thermal management. But as is with graphene, in many cases, there were additional benefits. In this case, it was reduced vibration and a dampening effect. So that's just one example. And that's in the Ford Mustang and the F-150, their flagship products. Within the automotive platform, pretty much any component or system is a target for using graphene from the tires on up. So you're looking at graphene enhanced elastomers or rubber coatings, anti-corrosion systems. Sensors is another really interesting part, especially as cars increase the use of sensors for all sorts of performance monitoring and safety features. Yeah, that's just a start. And of course, with EVs and the trend towards EVs, graphene enhanced battery and energy storage systems is another really interesting application. And another one alongside that, but for a completely different reason, would be the thermal management and the heat management of these batteries. So graphene has these really unique features of added strength, electrical conductivity, thermal conductivity, V protection, barrier properties that make it usable in a wide range of applications. And they don't necessarily have to have the same engineering objective in order for it to work.
Yeah, Terrance, sounds like you're more or less calling out that anything that's polymer or rubber based or coating based could use this as an additive. Is that a fair assumption to kind of broadly sweep across applications?
I think that is a fair statement. We've looked at the the plastics pyramid, if you will. Graphene can go into nylon. It can also go into PEEK. We look at graphene in coatings applications to make a paint tougher and more corrosion resistant. And the elastomers we talked about, we should not forget about all the seals and gaskets and other parts that need to maintain a seal and have to be also wear resistant as potential applications. And even another example where one might not think of this is in the motor oil or lubricating oils, that graphene is a natural lubricant and can be used at very small load factors to improve the lubricity of materials. So it's really a versatile material.
Can we dial in on that one with lubricity for a second? Because this one kind of hurts my brain a little bit, Terrance. To be honest, right? You look at, let's take, for example, the heavy duty diesel market, right? And we've got a lot of additives in their motor oil, and you have a lot of issues that OEMs fight for foot load, right? And so with the compression ignition cycle and these end gases kind of making their way past it, then getting into the crankcase and eventually ending up as carbon load in the oil. Is there something special here in the magic of graphene that realistically changing that to where, not all carbon's the same? And that's, I guess, what I'm thinking.
And I think you hit the nail on the head with the last statement. Not all carbon's the same. Graphene in particular is sp2 bonded carbon. It's not an amorphous carbon. It's also at the nanoscale, so it's not at a macro scale or the size of some of these particulates or particles. And the nature of graphene is that these are individual atomic carbon sheets that lay on top of one another and are connected by the weak atomic forces or the van der Waals forces, which are easy to slip. This is why if you take a piece of pure graphite and you rub it in your fingers, it feels oily or slippery. It's because those individual carbon layers are sliding off of one another. And so it has this really interesting property that it has natural lubricity because of that sliding, if you will, of the atoms over one another. And at the same time, coating the metal structures, the graphene is 1/3 of 1 nanometer in height, in thickness. So you've got this, nanoscale film, if you will, that also helps to protect the parts which it comes into contact with. So it's kind of counterintuitive. A lot of folks would say we're trying to keep carbon out of these systems, but graphene, because of this specific morphology, actually has a beneficial effect. One of the other questions I've been asked about this, especially for motor oil, is if the carbon will settle out, if the graphene will crash out of the oil that it's suspended in. First of all, it's a really low load factor, sometimes less than 1% by weight, so not very much material. And we've had examples where this has stayed suspended more than a year in storage. So I think that it, kind of anticipates some questions that some folks might have about using graphene in lubricating oil.
Is it bond to the metal? Because there's a lot of carbon content out there and a lot of steel that separates it from elemental iron, right? Should we get an actual bonded layer that will build on some type of, iron shaft, of some sort, as long as it's, steel and has enough carbon kind of exposed on the surface? Do we know enough about that?
That's a good question. And to be honest, I'm the executive director of the Graphene Council, but I'm not a physicist, PhD, or a chemist. We do work with thousands of folks that are in that field. My understanding, though, is we don't have covalent bonding between the graphene and the metal structure, but you would have these, again, these van der Waals forces that would have it coat. And the format of a graphene platelet, you think of it as like a, one card out of a deck of playing cards. So it's very flat, very thin, and in a wide platelet. And what happens for the anti-corrosion is that these platelets would lay down on the surface and create, the tortuous path for gases or for corrosive material to get to the underlying metal. But my understanding is we don't actually have covalent chemical bonding to the surface. More, it's these weak atomic forces.
Gotcha. So the guys that are listening that might do, DLC coatings, which is the diamond-like carbon coating, might not go out of business here in this one. But I think there's a few other things to really ask about here, right? When it comes to the polymers portion, you know, is it covalently bonded in the polymers then, and just not to the metal? Do you know that?
So that's a little more complicated. And this is where functionalization comes in. So we have a company that specializes in functionalized graphene materials, and that company would be Mito Materials based in the United States. And so functionalizing graphene means adding a molecule or a chemical to the surface or to the edges of it. Sometimes that's done to help it disperse better in a host material, but in other cases, it could be the bridge between the graphene particle and the matrix in which it finds itself that would be covalently bonded. And so it creates this really strong structure. The other aspect about graphene and these kind of composites, and what makes it an interesting material, graphene is a crystal, but it has a 20% bend radius. So you got some flexibility into this extremely strong material, which otherwise typically would be quite brittle and you'd get cracks. Graphene in the opposite direction actually helps to stop micro cracking. That's where we see, especially if you want to talk about hydrogen and pressure storage vessels, we have graphene that's used in these high pressure storage vessels for hydrogen. And one of the reasons is to stop the microcracking. And the other one is for the barrier properties, because hydrogen is notoriously good at finding a way out of a container.
That to do, with here's a website with cool facts that I looked up and prepped for this, right? And one of the cool facts was that graphene actually shrinks when it's heated. Is that part of the function here that's stopping these micro cracks? Is that like a good characteristic for polymer?
Well, and I'll be really open and transparent with you. I've not seen any of our experimental data that graphene shrinks when it's heated. So I can't really speak to that. But what I would say is the barrier properties, if you kind of think of these particles or these plates lay over one another. And so the space between those layers is what becomes quite difficult for molecules to pass. And if you had a perfect defect-free sheet of graphene, hydrogen cannot pass through it. So that's the reason why it's giving this. And then the microcracking, the graphene particles themselves are so strong that they resist those forces, those tensions in the material. So when it starts to crack and it comes up against a graphene particle, the crack can't propagate further. So that's the dynamic that's happening there.
Cool. Does it help for, they talk about these self-healing materials and stuff too. Is that any of that too with the crack propagation? To do any of that stuff? Or is that, a marketing term from some of this stuff? Or is it, that might help at higher loads?
Well, self-healing itself is quite an interesting concept. And we do know, I think you may have seen recently, there was an article about, Roman concrete and why does it last so long? And they found out that, because of the particular chemical mix, there were compounds that once they're exposed to water, they redissolve and then resolidify. So it is a self-healing kind of form of concrete. We haven't really seen that with graphene, not necessarily that's what's going on. It all comes back though to the fact that graphene is a material, it's chemically inert, extremely strong. And if you use it at very, very small amounts, it can have a big impact on the host material. And to give you a very specific example of this, we recently did a very exhaustive test of 15 different types and forms of graphene. And of course, we talked about there's different types of graphene. We took 15 different kinds and did a blind test, put it in a 2-part epoxy resin system that's commonly used for composite parts. And then we tested the mechanical strength, including, tensile strength and also impact resistance with a notch test. And we found that 1/10 of 1%, just 1/10 of 1% of the graphene material in this matrix led to as high as a 40% improvement in strength with a negligible negative impact on impact resistance. And as you make a material tougher or stronger, often it becomes more brittle. And so you get a degradation in the impact resistance. And in this case, we had a 40% improvement in strength. and a very modest, almost negligible change in the impact resistance at just that 1/10 loading. So that those are the kind of things that make this material so exciting.
You're talking about a fractional additive that, kind of falls into these categories of, you know, plasticity, changers or any of these. So this is smaller than some of the mineralizers in terms of load contents that I've heard of for kind of filler material for plastic, right? And so you're saying that essentially on a very basic level, using a little bit of this, kind of like salt in your meal, kind of changes the flavor of what you make.
I think that's a good analogy. And the counterintuitive thing about graphene is that if it's not working, try using less of it. And we've seen this over and over again. People would use graphene at 2% or 3% or 5% in a composite. And they said, it doesn't work. I'm not getting any results. And typically, if you talk to anybody about this, you're experimenting, you would think, well, it's not working. Let me see if I add a bit more, if I get a better result. In graphene, it's kind of the opposite. We keep working back downwards and lowering the concentration. However, that does increase the need to make sure you get an even distribution and dispersion of the material because you're using less and less and less of it. But the other impact of that, there's a couple of really important impacts that one should really think about. First of all, you're able to use a really small amount of it, which means you're not displacing other material that you want for a positive effect. Like a lot of times people are using carbon black as a filler. Well, the load of carbon black might be 20, 30, or even higher percent as the total part, which means you're giving up good material that you want originally to use that's being taken up by the carbon black. So you get more of the host material and you keep those properties. The other thing that's super important from a production and an engineering perspective is when you're adding graphene, it's a drop-in solution. You're not adding another processing step. You're using it as a nano additive, but you don't have a separate, bit of processing equipment necessarily. It's going to be able to use your same processes. So there's pretty low barriers. And at that really, really, really low load factor, even a high nominal cost on a per pound or per kilo basis means that the end cost into your finished part is also quite low. So from that point, it's exciting because unfortunately, the perception of a lot of folks because of the early days of graphene is that it's just too damn expensive to work with. And then they don't even, it's not even considered. And it's because most people don't know that you can use such a small amount of it and still get a significant material improvement. But when you put those two together, it's a pretty compelling argument to get a big performance lift for an acceptable cost and without a massive change to your process.
That sounds like an engineer or entrepreneur's dream from what you're laying out there, Terrance, in terms of, hey, I have to invest very little, but I get a large return here. And if you're saying that it's such a fractional amount of the total heat cost of raw material at a 0.1% load, and I'm increasing strength, then, maybe there's some other way for lightweighting or durability of components. That maybe there's some case studies that we could go through one at a time on interesting applications where, essentially, you put in this load factor and the graphene itself isn't really the direct cost reduction, but maybe the knock on is really a game changer.
Yeah, you raise a great point, and there is a good example of this. So there's a company in the UK called Briggs Automotive Corporation, or BAC, and they make a street legal monocoque. Basically it's a sports car that's all carbon fiber panel, and they use graphene in
the BAC mono. Is that what we're talking about?
The BAC mono, a lovely piece of automotive hardware that uses graphene in those panels. And what they were able to do is to remove a ply of carbon fiber, lightweighting, while maintaining the strength. So now you're saving money on the carbon fiber raw material cost, but you're also saving time and money on the layup. And you get a lightweighted automobile at the same time. So, it's a win-win-win. And you're absolutely right. You do have this added cost of the graphene material, but you have directly offsetting costs from other materials saved. And then on top of it, you reach your engineering goal of lightweighting.
That sounds great to me. Coming from a math engineering background, it was always a dollar per kilogram basis. How many dollars do I have to spend to go ahead and reduce weight? But, from what you're saying, in some of the edge cases for carbon fiber, especially, removing a whole layer and a whole layup process is a net cost save. You talked a little bit about tires. Is there something there in terms of durability or anything game changer there? Because, to me, tires are the original carbon black story in terms of automotive use. So what's graphene doing for tires?
Again, really, really good question. And a real world example, strong one, it happens to be in bicycle tires, but still it's the same technology, right? You're talking about elastomers and road tires. Since the beginning of time when rubber was first made, there was always a trade-off between durability and wear and friction. So if you wanted a longer wearing tire, you usually had to give up friction. You make it harder. Anybody who watches F1 will recognize, the hard, medium, and soft tires that are used, and they have corresponding life and duration. The soft tires not lasting very long, but they give you that grip. They give you that friction. So it's been a rule that you want better friction, you're going to give up durability. Adding graphene, the Vittoria bike tire company, which is an Italian company, makes high-end performance bikes and tires for road racers, have added graphene now for several years. And the result is that you get a longer wearing tire, you've got less roll resistance, but it doesn't sacrifice friction. So it broke the rules on, what was a given in making a tire. If you want it to last longer, you had to accept that you weren't going to get as good friction. And that's no longer true. You can get both.
Awesome. There's got to be something hidden in there for thermal then, right? There's got to be a catch hearing where, the tire doesn't transfer heat properly or something. I'm messing with you.
No, it's a really good question. In that thermal transfer property though, Ed, is another reason graphene's used. We have companies using graphene purely as thermal spreaders, whether it could be things like LED lights or, in a heat sink where you're trying to, take heat away from a heat source and dissipate it. Graphene is more thermally conductive than aluminum or aluminum. And it also can be put in extremely thin form factors. So, think of phones and laptops and these kind of devices, but in the automotive compartments with sensors and lights and everything else, and you need heat sinks. And it can be put into these films so you can get around bends and, complex shapes. It's a really good heat sink, which, for graphene with all its versatility, sometimes a really simple use of just as a heat sink is a really good application of it.
Yeah, I've seen little pads that they'll sell for graphene heat sinks and stuff. Is everybody going that way? Those things it seem a little expensive and hard to place for, the PC build out. You get this little black pad, you got to put it there. Is that the same thing you're talking about, or is it loadable in standard thermal paste? Or is it, something where you're just gonna apply it to the normal heat sink itself, or you know more about this use case?
So it does depend on the exact application, but for example, it can be made into a heat spreading film and cut, die cut to particular shapes. It can also be made into a paste so that you can use it in that way. The other related application that comes to my mind, we haven't discussed yet, and I know we're talking about thermal right now, but also electrical conductivity in adhesives. So if you want to maintain for anti-static, for example, the fact is that graphene can be engineered into an adhesive. It can be engineered into a paste, into a film, all these different form factors. so that you can exploit these thermal dissipation properties or electrical conductivity, at least to the point of anti-static type of behavior, if not, carrying a current.
I guess, maybe that means, some of these adhesives for joints and body structures or something else. Um, is the same behavior for loadout um, in a percentage basis applicable to some of these dealers and adhesives you said? Meaning you get significant rises in electrical conductivity with that percent or whatever you're loading in.
You would need a higher percentage of the material to get to the electrical conductivity or for the thermal conductivity. But that doesn't necessarily mean it's going to be inordinately expensive, because there are a range of graphene materials in terms of cost as well, um, to address these kind of applications. The short answer, Ed, is you do need more graphene as a percentage of the matrix to get the electrical conductivity, because you need more of the parts touching one another, if you will, these individual nano parts. And the same goes for the thermal conductivity. It's not the same as for the strength improvement.
What are the case studies looking like in terms of part cost, right? So I start out, let's take the Martin Rea type of brake line example, right? They get to use, shorter lines and run it weird areas and all this other stuff. I think that was a Ford example too, but if it's really impacting panels or durability or anything like that on a attributable basis for cost. I mean, is it, a penny a part? Is it cost savings because you use less material? But, for the listeners that are, let's say, material geeks, what's kind of the bottom line cost structure?
Yeah, it's a good question. I understand it. And I'm afraid I'd have to tell you that most of this stuff is, that's commercially quite sensitive.
Yeah.
And it does depend on the actual part, right? So, we can talk about rough prices, in the market for these materials. One can figure out if you're using it at a low weight factor. But let me answer the question this way, Ed. What we've seen, and you've kind of touched on it already. You could do a very simple, what do I have to pay to get graphene into it? If it lets me save some of the original host material, what is the cost savings? And then you see what's under the line there. But what we've found, like in the example with Ford, where they got not only a better thermal product under the hood, but they got dampening and a quieter ride in the cabin, right? Less vibration. There are often these knock-on benefits. We've had people who are doing extruded parts, right? And there's a limit to how fast or how many parts you can do through the extruder. That then you add graphene to add strength, and guess what? You get better lubricity through the extruder. Now you can do a higher throughput. That's money, right? So and there's other examples where graphene was added to the polyurethane to make it stronger, and it also made it more fire resistant, right? So now you've got better fire retardancy, which is in the particular application was a very valued benefit, but that wasn't the original intent. So, what I would say to anybody who's thinking about this, if you have a particular engineering challenge and you think, added strength or thermal conductivity or electrical conductivity or lightweighting is your primary objective, graphene is definitely worth looking at and working with a good graphene producer or expert on attacking that application. And what we haven't seen to date, and this is also kind of astounding, but because graphene has so many beneficial aspects to it, it's not a one-trick pony. We have yet to really see, okay, where's the main trade-off? Where is the negative part of the performance you have to accept in order to get the gain in another area? And surprisingly, I'm hard pressed to think of an example where somebody said, okay, we improved strength, but we lost X, right? So, it's worth looking at. Now, having said everything that we've said, I also want to let people know, because there are so many types and forms of graphene, it's important to get the right one for your particular application and for the material that you're putting it into and how you're using it. And so that's where the rub is for people to, make sure you invest the time to get the right graphene, because if you get the wrong material or you're not working with a partner who can do the application correctly or do the dispersion, you're not going to get a good result. And it's not because the graphene doesn't work. It's because the process wasn't correct or it wasn't tuned properly. But that's probably at this point, it's not really cost anymore. It's more about taking the time to do the application development, to tune the material to the application.
Very
Really
good.
well thought.
Thank you, guys. Thank you to both of you. And unfortunately, that's all the time we have for today. A big thank you to you both for joining Autology.
My pleasure, Anna and Ed. Thank you for having me. I hope this was interesting for your audience, and I would encourage anybody who wants to learn about graphene and what it can and can do is to contact the Graphene Council as a neutral source of information, and we can connect you with experts in the field if that's what you need. So thank you for having me.
Thanks for running that, Donna, as usual. And thanks, Terrance, for having a good open discussion today.
My pleasure.
Yes, yes, indeed. And thank you to all you listeners for tuning in as well. We'd love to hear your thoughts on today's episode at our autology@spglobal.com email. And you can find out much more at autotechinsight.ihsmarket.com. Don't forget to hit all the subscribe, follow, and like buttons to stay on track with the latest Autology podcast. And we look forward to you joining us again in the next episode. Bye for now.